Welcome, Mr. Sutton bringing you the AB Calculus 2-7 Extra Practice Number 2 solutions on Intermediate Value Theorem. On this one, we're told that f is a function such that f of 3 is less than 4 is less than f of 5, and we want to know what additional information we need to say that there's an x value on the interval 3 to 5 that plugging it in gives us 4 back. Okay, so this is talking about the Intermediate Value Theorem when you're trying to guarantee there's some y value between two x values that equals a certain number. Intermediate value theorem, we need the value you're looking for to be sandwiched between the beginning and the ending y values on the interval, which is what this first statement is saying. We also need one other important thing. We need continuity on the interval in question, on the closed interval in question. It's not enough to say that we're starting with a number that's less than 4 and ending with a number that's bigger than 4. We can't guarantee we go through 4 unless we're guaranteed to hit all the y values in between, and that's what this continuity does for us. So that's going to be choice C. On this problem, we've got this f function equaling x plus tan of x over 5 minus 10, and the IVT applied on the interval from 12 to 15, they're saying is going to guarantee a solution on that interval to which equation? So basically we're asking, the IVT guarantees which of the following y values is on my function on the interval from 12 to 15. So in order to use IVT, we need to establish two things. First off, we have to know that our function is continuous on the interval they're giving us. Now, they didn't have an option for does not exist or something like that, so we're probably guaranteed that we're continuous, but just to double check it here. The only issue with continuity with this function, I mean, x is fine, negative 10 is fine, but tangent, we know, has asymptotes when you're taking the tan of pi over 2 or 3 pi over 2, or really any angle coterminal with that. But let's start with pi over 2 and 3 pi over 2 as being our problems here. So if x over 5 then has one of those values, we're in trouble. So what x values would this be? Well, let me just multiply each of these by 5 and see what the decimal comes out to. This is a calculator problem, so here we go. So if I multiply 5 by pi over 2, that ends up giving me about 7.854 and some change. And then let's take a look at 5 times 3 pi over 2. So I'm just finding the locations of vertical asymptotes on this function. So let me go yank my input from before, and let me make this, let's see, pi times 3. I think I can put a 3 there, and that comes out to 23.562. Now why do we care? Well, if these are our asymptotes, take a look at where our interval is, 12 to 15. So this is completely contained between these asymptotes, meaning there are no asymptotes that are on our interval. If there are no discontinuities on the interval, that proves that our function is continuous on the interval from 12 to 15, which is what we need in order to use the IVT. The other thing we need for the IVT is whatever one of these y values you're proving is on your function, you have to show it's between the starting and ending y values for your function on this interval. So we need to figure out f of 12 and f of 15. Let's go ahead and do that now on the calculator. So first off, to make my life a little bit easier, I've taken this function and entered it as y1 in my y equals. Now let me quit out of there, do alpha trace, pull up y1 from that menu, and I'm just going to plug 12 into this. And whether you close the parentheses or not is up to you. But if you plug in 12, that's about 1.084. And now we also have to find f of 15. So let me just go back on the calculator, yank that input from before, and let me replace that 2 with a 5. So now we're doing f of 15 here, which is going to come out to about 4.857. All right, so the IVT guarantees that there is some c value between 12 and 15 such that f of c is between 1.084 and 4.857. So which y value out of these answer choices is supported by the IVT? Well, negative 10 isn't quite there. 0 also is outside this interval. 4, however, is between these two numbers. 14 is not, so 4 is the only one that works. Choice C. For this one, we're told that f is a function of x, and we want to know which statements, if true, guarantees there's a c value on -2 to 3, where f of c equals 10. If we're trying to guarantee that we get a certain output on a function over an interval, you're basically talking about the Intermediate Value Theorem. The IVT guarantees that we'll be able to find this magic c value, provided two things. First off, our function needs to be continuous on -2 to 3, so that I'm guaranteed I go through all the y values from start to finish that are on that interval. So we need continuity on the closed interval, and we also need to make sure that the y value we're looking for, 10 in this case, is somewhere between the starting and ending y values. So in this case, between f of -2 and f of 3. If we meet these two conditions, IVT guarantees we'll find a place where y equals 10. Okay, so let's look at our answer choices. Choice A is talking about the function being increasing. That by itself is not going to be enough. We need continuity. Same thing with choice B. So it's down to choices C and D where we have continuity on the closed interval. And now 10 needs to be between the two values. So for C, -2, f of -2 is 0, f of 3 is 20. 10 is between 0 and 20, so that's good. But let's just consider choice D. We're starting at 15, ending at 30. We're not guaranteed to go back down and hit 10 going between these y values. So then we have to go with choice C, 0 to 20. On this one, we have this function f of x equals 2x plus tan of x over 5 minus 15. So that's a big mess. The IVT applied to f on this closed interval from 10 to 15 guarantees a solution to which of these equations. So basically we're asking which of these four y values are we guaranteed to run into if we start looking at this function on the interval from 10 to 15 for x values. Okay, so to use the IVT, we need to do two things. One condition is we need to make sure that we are continuous on the closed interval in question. And after we do that, we need to make sure that the y value we're looking for is sandwiched between the beginning and ending y values. So let's deal with the continuity piece first. For this to be continuous, we have to look at each piece of this function. 2x doesn't have any discontinuities, it's just a line. -15 also doesn't have any issues. Where you're going to run into issues is this tan expression. We know that tan is undefined in some places. It has vertical asymptotes wherever you have an angle of pi over 2, because that's a perfectly vertical slope, or 3 pi over 2, or negative pi over 2. Really, anything that is some multiple of pi away from pi over 2 or 3 pi over 2. So in this particular case, we're just going to need to worry about pi over 2 and 3 pi over 2. So we know that we have vertical asymptotes if the input, which in this case is x over 5, equals pi over 2 or 3 pi over 2. So let's see what x itself would have to equal to get these vertical asymptotes. And the reason we're looking for discontinuities is if we can figure out where those are, then we can see if any of those are inside the interval. And if they're not, then we know we're continuous on this interval. So multiplying each of these things by 5 to get x by itself, let's see what we get. So if we do 5 times pi over 2, and I did alpha y equals to get my fancy fraction there, let's see what that comes out to. About 7.854 if we round that off. Okay, let's also multiply 5 by 3 pi over 2 to see what that's going to be. And I'm just going to go up here and yank my input from before, and instead of writing pi, I'm going to write pi times 3. I think I can do that. Yep, so that's going to be about 23.562. So taking a look at where these asymptotes fall, it looks like neither of these are on the interval that we're looking at here, 10 to 15. In fact, this interval, this whole interval, is between these asymptotes. So we've basically shown that we are continuous on the interval from 10 to 15. Outside of that, all bets are off. But inside here, we know we're not going to be skipping or jumping around. Okay, next thing we need to do is figure out the beginning and ending y values on the interval from 10 to 15. So we need to figure out f of 10 and f of 15. Let's do f of 10 first. So to make my life a little bit easier on the calculator, I've gone to y equals, and for y1 I've actually plugged in this function because I know I'm going to be using it at least twice. So let me go ahead and do that. And then quitting back to the main screen, Let me do alpha trace to bring up my y1 menu here. Enter, and then let me use parentheses and a 10 to plug 10 into that function, giving me about 2.815. All right, now we need to figure out f of 15. So let me go back and yank my input from before. We're doing y1 of 15 now. Comes out to about 14.857. So we're looking for a y value that's between these two values. Any y value between these two will be guaranteed to be on the interval from 10 to 15 by the IVT. Looking at our choices, negative 15 is too low, 0 just misses the cutoff, 5 is in there, 15 just misses the cutoff in the other direction, so the only one that works is choice C. So we're guaranteeing something between these two numbers. Choice C does that. On this one, they're telling us that f is a function such that f of 5 is less than 6 is less than f of 7. We want to know which statement provides enough information to say that there's an x value on the interval 5 to 7 such that plugging it in gives us back a y value of 6. So basically, when you're trying to guarantee that you get a certain y value on some function on some interval, you're talking about the Intermediate Value Theorem. Now, this theorem has two conditions. One of them is that the value you're looking for has to be sandwiched between the beginning and the ending y values. That's what this f of 5 less than 6 less than f of 7 statement is all about. F of 5 is the first y value, f of 7 is the last one, and we're saying 6 falls somewhere in between those points. Now, this guarantees that 6 is actually on this function in the interval, provided one other condition, and that is that you have to have a continuous function. IVT requires continuity on the interval, the closed interval, that you're dealing with, because it's not enough to go from something that's less than 6 to something that's bigger than 6. You also have to be guaranteed you're going to hit all the values between these y values. So once we've guaranteed continuity, we've got enough information to make this conclusion. So then, choice C. On this problem, we have the number of fish in a pond modeled by this n of t function up here, and we're also given that this random f function, which is one of the sub-rules, is a continuous function, and that f of 0 is 80. So based off of all this, we want, first off, the limit as t approaches infinity of n of t. And then what does that all mean? Well, if we're approaching infinity, that means we're moving to the far right. So that means out of all these rules, we only need to consider the rule for t greater than or equal to 8, because that's where positive infinity is somewhere beyond 8. So we just need to take the limit of this expression as t approaches infinity, and the limit of this expression with infinity, we can ignore these slower growing terms. So choosing our champion here, in the numerator, we only need to consider the 80t. In the denominator, we just need to consider the 0.05t. So we have 80t over 0.05t, which reduces to, let's see here, 80 divided by 5 would normally be 16, but this is 0.05, so that's going to be 1600. And what does that mean? Well, that means since this function in general is modeling the number of fish in a pond, that means that as time increases, the number of fish in the pond is approaching 1600 fish. For this part of the problem, we want to know if the function n is continuous at t equals 8, which of course happens to be a border value. So we can't rely on the continuity of any one rule. We kind of have to make sure that we're continuous from the left and the right. So let's take a look at the left side limit. Then we'll look at the right side limit and the function value at 8. So left side limit of n of t. We're using the rule for values less than 8, immediately less than 8. So that's going to be this middle rule here. We're just going to plug 8 into this t, so we have 25 times 8 plus 150. 8 times 25 is 200. Add that to 150, we've got 350. Now for the right side limit, we have to use the rule for values immediately greater than 8. So that's this third rule. Plugging 8 in there, we have 200 plus 80 times 8, all over 2 times 0.05 times 8. And this was a no calculator problem, so this is going to require a little bit of arithmetic finagling here. In the numerator, we've got, let's see, 200 plus 640, so that's 840. Denominator, well, 0.05 times 8, 5 times 8 would be 40, but this is 0.05, so moving our decimal, we've got 0.4 plus 2 is 2.4. And, oh, that's going to be fun to simplify. Okay, well, little trick we can use here. We can multiply the numerator and denominator by 10. So we can call this 8,400 over 24. So now we don't have to worry about a decimal. And then let's start reducing this. So not really sure how much I can reduce this by off the top of my head, but I'm pretty sure 4 goes into both of these. So 24 divided by 4 would be 6 in the denominator. In the numerator, this would be 2,100. And then again, I'm not sure exactly what I can reduce this by, but let's reduce this again by 3 now. I mean, there's no need to go all at once here, right? One piece at a time. So 2,100 divided by 3 would be 700. 6 over 3 would be 2. So this is really 700 divided by 2, which now I'm a little bit more clear about this. This is really, after all, 350. So the left and the right side limit agree, and n of 8 is going to be equivalent to the second function here. So then this 350 that I just found, I'm going to say that this also equals n of 8, and I do have to show this. I do have to explicitly show that I have considered the function value at 8 in order to make any statement about continuity. All right, so now that I've identified the limit and all that stuff, I know that the two-sided limit at 8 and the function value at 8 are going to match up here. They're all 350, so that tells me that my function n is in fact continuous at time 8. For this problem, they're telling us the function is continuous at time 6. They want to know if there's a time between 0 and 6 inclusive, where n of t equals 250. If we're asking if there's somewhere on an interval where we get a certain output value, generally we're talking about the intermediate value theorem in those situations. So to use the IVT here, I need to show that I have continuity on this closed interval, and also that this 250 is between the starting and ending y values for this function on this interval. So let's start by figuring out the continuity piece. So from 0 to 6, well, I know that from 0 less than or equal to t less than 6, we have the f function, and they told us that f was continuous. F is a continuous function. So we have continuity of f, and we are also given that n was continuous at exactly time equals 6. That is enough to prove that we have continuity on the closed interval from 0 to 6. Which means that my IVT will work if I have the correct starting and ending y values. So let's talk about those. I need to know what n of 0 and n of 6 are. N of 0, that's going to be taking, let's see, f of 0 basically. F of 0, they told us, is 80. So n of 0, which is really f of 0, all of that is 80. Next, we need to talk about n of 6. So for n of 6, we have to use the rule where t equals 6. That's this middle rule here. So we're doing 6 times 25 plus 150. That's 150 plus 150, which is 300. And now the important piece here, we were looking to guarantee that n of t equaled 250 somewhere on the interval from 0 to 6. Well, if you're starting at 80 and ending at 300 and you have a continuous function, since 250 is between the starting and ending values and you're guaranteed to hit all the y values in between because we have continuity, the IVT guarantees that you're going to find the t on 0 to 6 that gives you 250 as an output. For this free response problem, we're starting with this mass of yeast in a culture, and we're measuring this mass in milligrams, time in hours. It's modeled by this piecewise function up here, and we're told that f is continuous, and also f of 12 is 20. Given all this, part A of this problem, we want to find the limit of this function as t approaches infinity, and then explain the meaning in the context of the problem. All right, well, if I'm doing limit as t approaches infinity, that means I'm going to the far right, so I have to use this last rule here that takes over as soon as t equals 12, or at least is greater than 12. So I'm doing limit of this bottom rule. Now this is one of those choose your champion, keep the dominant terms kind of situations. 600 is the only term in the numerator, but as t approaches infinity in the denominator, this is really 10 over e to a positive power, which is going to be essentially 10 over infinity as this keeps growing. So you're really just doing 20 plus 0 when all is said and done. this 10 over e fraction becomes infinitely small. So we can rewrite this whole thing then as 600 over just 20, because again, this exponential term is going to 0. And 600 over 20, if you wanted to, you could reduce that to 30. So that's going to be, since we're talking about the output for the y function, that's going to be milligrams. So 30 milligrams. So our limit is telling us that as time increases, the mass of yeast is approaching 30 milligrams. For this part of the problem, we want to know if y is continuous at t equals 12 and then justify the answer. So to show continuity, we need to show that at 12 the limit exists, the function value exists, and that those two things equal each other. So for the limit, let's do the left and the right limit to see what those are. Left side limit as t approaches 12 from the left of y. We're using this rule here that has t less than or equal to 12. So when I'm doing this, I'm basically plugging 12 into this rule, which means I'm doing f of 12. Well, what is f of 12? We don't really know much about f except for the fact that it's continuous, so the limit of f and the function value of f are the same, and that f of 12 is 20. So that means that this quantity here is exactly 20, and we can move on to finding the right side limit at y. Right side limit for y at t equals 12, we're going to be using this t greater than 12 rule, so basically plugging 12 in for t in this huge expression here. Well, let's see here. This is really 0 times negative 0.05, that's 0. So we've basically got 10 times e to the 0 here. And that's just going to be 10, right? Because e to the 0 is 1. So we've got 600 over 20 plus 10, 600 over 30, also comes out to 20. So this establishes that the limit exists. One more thing we have to figure out is the function value and whether or not it also equals 20. Now the function value, that's what happens when we are plugging in exactly 12. Y of 12 itself is just using this middle rule, which again gives us f of 12, which again gives us 20. So what we did up here for the left side limit is the exact stuff we would do for y of 20. So I'm just going to write equals y of 20 to kind of piggyback on what we already did and show that, hey, this is also the value of the function at 12. All right, so now we've showed that the limit as t approaches 12 and the function value at 12 equal each other. This proves, since they both exist and equal each other, that y is in fact continuous at time 12. For this last part of the problem, they're telling us that the function y is continuous at time 10, so at this border value here, and they're asking if there's a time between 0 and 12 at which y of t equals 18. Justify your answer. Note that you didn't actually have to find what time it was, you just had to prove that there was such a time. So this is going to be an intermediate value theorem problem if you're trying to show that you get a certain output over some interval. So for intermediate value theorem, IVT, we need to show continuity, or at least know of continuity for the whole closed interval, and then we need to show that the value we're looking for is between the starting and the ending y values. Let's start with continuity. So starting over here at 0, this 10e to the 0.05t function, this is an exponential which is known to be continuous. They're telling us that we are continuous at time 10. So the crossover from one function to another is handled smoothly by them just giving us that continuity. And then finally, from 10 to 12, we know we are continuous there because f of t, they told us, was a continuous function. And then finally, because we need the closed interval from 0 to 12, we know that we are continuous at time 12 because, well, we just proved that in part B. So we have continuity then on the entire interval from 0 to 12, handled kind of piecemeal, but we cobbled it together from different parts. Next, we have to figure out y of 0 and y of 12. For y of 0, the beginning y value, we're going to use this first rule here. So that's just 10e to the 0 basically, which is just going to be 10. And then we need to find y of 12. We already found in part B that y of 12 was 20 because y of 12 is just f of 12, which they told us is 20. So here's the important part. 18, the value we're looking for, that's between 10 and 20. This is important because if you have a continuous function, you can't get from y equals 10 to y equals 20 without also going through y equals 18. So by the intermediate value theorem, we are guaranteed then that we have a t on 0 to 12 such that y of t equals 18.